So we're going to get started. This is 42, the answer to life, the universe, and everything offensive security. In this, we're going to talk about the offensive use cases of machine learning, and it represents probably the last year of our research. At least mine, or ours, yeah. I'm Will Pearce, Muhax, and I'm a senior operator at Sandbox Security. And my job primarily focuses on research, training, and ops.
And my name is Nick Landers, or Monarch's Gas on Twitter, and I'm a team lead. I do a lot of research, dev, ops as well. And yeah, I would say to introduce me and Will is definitely the ML lover and is really passionate about the field. I would say I carry a little bit more skepticism. So we're going to hopefully do a bad cop, good cop situation and balance each other out as we go through this presentation. So first, we need to sort of make the jokey slide about what is ML. If you walk through the vendor booth of Black Hat, you'll see exactly what we mean. There's a lot of booth babes yelling out datasheet keywords like next generation, scientists. I've even heard central cortex thrown around, which is pretty rough. But it's effectively a lot of magic that gets investors, goes public, and makes a lot of money. People make the joke it's a bunch of rebranded if statements. But as we know, this obviously isn't the case.
So what really is ML? So in my mind, ML is just a set of techniques that aim to model a problem mathematically. And so it rolls up stats, maths, and computer science into one kind of overarching field. And it's not new, so it's actually a pretty old discipline. We think it's new, and it is new to us. But it's been around for a while. The term machine learning was coined in the 50s by a scientist at IBM. But effectively, it gives us predictions without explicit programming. So predictions being maybe rules that we get without the program being explicitly programmed to do so. And it's growing fast. So people just have so much data, and then they're not really sure what to do with it. And so machine learning has kind of come along and been that catalyst for data utilization for organizations. They've sort of realized the power of it, and they've just applied huge amounts of compute. It's still magic, so even when you get into the math, it's still magic, but it is still mostly just math. But why do we care? So we care because it's coming to a product in a field near you. Literally everybody is applying it in their own ways. So whether it's information security, healthcare, industrial control systems, like everybody is implementing it into their systems. And it's no longer a math problem. So, a while back it was like, well, our algorithms aren't as efficient as they need to be, so this is cool, but there still need to work. It's no longer a math problem now. It's just an engineering problem. So it's how are these systems being implemented? And our future, we believe our future is going to be fought with ML. So, for example, in the future, you're not going to have to bypass one model. You're going to have to bypass a model at every stage of the defensive process. And it can be really, really awesome. So you can get good results with relatively small amounts of data, if the problem is very specific. But it can build relationships in non-concurrent data. It can bring out like those operator sixth senses. So, how do I know which file share to look in? Like what is it about a file share that gets my query into the host. And it can go through just massive amounts of data way faster than any human can scroll through. So it can very quickly bring you insights that you previously wouldn't have ever gotten to had it been a manual process. And then we're going to just describe offensive ML. So offensive ML is literally just the application of machine learning to offensive security problems. And there are a ton of projects out there already. And yeah, you should go to them and have a look. It's a growing field, and highly recommend looking at all of these. We're going to discuss abusing control relationships, so sort of a bloodhound without bloodhound. We're going to discuss detecting sandbox environments. So if any of you saw the B-Sides talk, we'll go over that. And then we're going to talk adversarial ML, where we steal a model for evasion. So we're going to get into the basics collision course. So starting with ML, you can literally Google any tutorial, and it'll come up with something. And so if you want to spam classification, just Google spam classification machine learning. If you want to detect cats, if you want to detect dogs, if you want to literally do anything with ML, there's a lot of weird stuff. And here we just have a bunch of links. So there is somebody in your field or your interest that's working in ML. You just need to find them.
All right, so talk a little bit more about the specifics. Obviously, the tutorials aside, the process generally breaks down like this, where the first two steps are arguably the most important by far. Data is everywhere, but what should we collect? And usually we're trying to use that data to answer a problem. So sometimes you have the problem that comes first, and then you ask yourself, what data do I need to collect to solve this? Other times the data is sitting in front of you, and you sort of ask what problems could it solve if we were to make it actionable. Step 3 is to process and extract useful features. So we call this feature engineering. We'll discuss that later on. 4 would be to just download Python plus a bunch of ML libraries. People have their favorites, but generally you'll see a lot of NumPy, Pandas, Scikit-learn, TensorFlow, and we prefer Keras on top of TensorFlow for the actual algorithm implementations. Step 5 would just be to write a 10-line script, which is not a joke. They're generally literally less than 10 lines, and ML your heart out. In fact, you can do ML in less Python than it takes to write a web server generally. So the case study that we first tackled when we started getting into this was Sandbox Detection, and Will went over this in his B-Sides presentation, but sandboxes hold a special place in our heart as offenders. They're obviously a dangerous place, and we do a lot of custom tool development, so getting our tools caught in a sandbox represents a huge hit to our operational effectiveness. So the popularity is rising, and we're trying to think about ways we can detect sandboxes with limited information. The very act of querying that information is going to make us look malicious, so we're trying to find minimal information to make the best decision possible about whether or not any particular host is a sandbox or not. So the data that we chose is just a raw process list. Obviously, the features you could have selected here, are very extensive, but a process list to us speaks outside of even the detection of a sandbox, and it's just a valuable bit of information that we already integrate into our toolkit. So a sandbox we collect for detecting whether or not defensive products are installed, or we collect them to get context around a particular user running, say, a payload. So if you were to look at this process list and start thinking about what features you might extract, you could start by saying, well, this looks like a sandbox because procmon is running. Certainly don't like that. And admin tac PC doesn't look like it's on a domain. The username is generic. So we can start building out features like a bad user count or the number of sysinternals tools running. But I think we can do better than this. We can start thinking about what we call meta properties of the list. So for instance, the process ID in Windows is an incremental identifier that generally goes up the longer the machine has been running. So we could take the average PID and use that as an indicator of how long the machine's been up, which could tell us something about a sandbox. We could also use what we call compression. So a lot of users on real machines have multiple processes running that look, they look repeated. So like Chrome opens up multiple processes for each tab and window. So if we took all of the process names and uniqued them, then we took the ratio between them, we would get a compression rate. And this tells us something about how many repeated processes are running on a particular host.
And then once we have that information, we need to feed it into an algorithm. So we need to effectively feature engineering that process of turning words into numbers such that we can introduce it into a network. And so when you finally get your features, we create our inputs. And so this is just a NumPy array with the rows being a sample. So each of these are sandboxes, and the columns being your features. So here we have process count, user count, and then the ratio between them. Then once we have our inputs, we need to label them. So labeled data in a supervised machine learning problem is huge. So we need labeled data. And we just went through manually. We don't have so many that we can't do it in a manual fashion. So we just went through and we labeled all of our sandboxes as, 0 is safe and 1 is a sandbox. And this is eventually what we'll target with machine learning algorithm. But binary classification 0, 1 isn't the only kind. So you can have multi-label where you're grouping sandboxes into like categories. So maybe you have a category for the United States, a sandbox out of the United States versus Holland or Ireland or wherever. So potentially you could get some additional insights that way. There's also another one that we'll discuss later, but it's just a regression problem where we're targeting a continuous variable. So for example, instead of 0 or 1 or some n categories, we're targeting 1 through 1,000, for example. But before we get into it, we're gonna just do a brief overview of a basic neural network. So the smallest unit of a neural network is a node, and nodes effectively carry values. And between these nodes, you have weights, and they represent the strength of a connection. And then inside of an output or inside of a hidden node, you might have some sort of activation function. And this gives some level of confidence or level of activation that the node represents. And then you have layers. So these nodes are distributed into layers. So you have typically an input layer where all your features go in. You have an arbitrary number of hidden layers that kind of pass activations to one another. And then you just have an output layer. And this, the number of nodes in each layer is going to differ depending on your problem. But then we have a network. And a network is just all those layers strapped together with weights. So those lines are the connections between. But when we want to calculate our network, we just go through. So you see we introduce our features, and these are scaled. So depending on your activation function, you might have to scale them. And effectively, it's just super simple math. So it's the weighted sum of the inputs passed into an activation function. Sounds more complicated than it is, trust me. And it's super simple. So then we just go through and we feed forward those calculations for every node in the next layer. And those inputs or those outputs, or those activations become inputs for the next layer. And we just do that until we're all the way at the end of our output layer. And then, so at the end, we have our output, which is effectively our prediction. And let's say this was a sandbox. Our target was 1. Our prediction was 0.67. We just subtract that, and then we get our loss. There are many ways to calculate loss, but at a basic level, this is what it is. And then here's the magic of machine learning is effectively, we need a way to take that loss and then back propagate it to update our weights. And so we don't have time to go through into back propagation here because it's arguably the heaviest part of it. But in the incoming weights contribute to the error in different ways because they're different values. And so back propagation is just that process of adjusting incoming weights to an output layer up or down such that the model learns. And so, for example, if we update our weights here in the last layer, and then we feed forward, we do those same calculations again using those new weights, we get a new loss, which is 0.25, and our accuracy's gone up by 0.08. And the code to do this is super simple. So when we're talking about like 10 lines of code, this is literally it. So this is a modeling Keras, and you'll get a neural network. So the results for our sandbox stuff, we had 130 samples. We had 18 known sandboxes. There were a few that we missed manually. But our accuracy, just from a very basic neural network, was really high. But there are lots of options for feature combinations, so you don't have to use. You can literally use anything you want, whether it's a 0 or a 1, true or false. The important thing is that they're numbers, and we'll get into more feature engineering later. But ultimately, it's a great problem for ML. So it's just a very simple problem that humans can do very, very quickly, and it was a good introduction for us. And so we ended up writing a tool that's just Deep Drop. It's a machine learning-enabled dropper. And I released it at B-Sides a couple weeks ago. But it effectively just holds a trained model that allows you to, it'll make drop decisions for you. So when the process list comes back, it's going to process it, and then it's going to give you some prediction on that process list, and then it's either going to drop your malware or it's not.
All right, so that's sort of our cheesily named collision course over with. So from this point, we're going to start tackling, some of the external challenges of ML and also look at some more complicated examples. But in that study that we just went through, we sort of glossed over a lot of the data collection bit, and it's going to become relevant, especially if you start to try using this in real offensive ops. So the primary issue we run up against initially is just that offenders traditionally don't keep data. In fact, in many ways, it's frowned upon, which is funny given the fact that vendors are allowed to keep data and then build algorithms off that data and then sell those algorithms back to the clients that were trained on their own data. We start to ask questions like how can or should we anonymize our data if there is proper ways to do so? And how much further could our field on the red side go if we were able to share data sets with each other and train on those data sets? In many ways, it's trying to teach somebody to use Bloodhound, but you have to have a test Active Directory data set so that you don't expose information about a real network. There are potential solutions for this that me and Will have thought about. Obviously, this list is a short sub-list of probably a lot of other solutions that people could implement, but one is we could only keep the model weights themselves, so we just looked at how we would train a sandbox model, and we would continue doing the process of feeding forward and backpropping until our accuracy rate was something acceptable, like for instance 95%. Once we got there, we could effectively save the model and all of those weights and delete the data that we used to train the model with. In the future, the model is trained, albeit on legacy data, so to speak, but we can use it to detect sandboxes in the future. So this is going to vary depending on how the data deviates over time. We could hash our features for like storage. This is obviously a loose solution that has bypasses for it, and it speaks to a lot of things about domain-specific knowledge. So obviously the more familiar you are with the features themselves and maybe how they were hashed, the better you might be able to extract the features from the hashes if you got access to them. We could also just use models that don't require previous data. This is something like Levenshtein distance that we'll talk about, where the model itself doesn't necessarily need to be trained. It's effectively some algorithm that gets ran against data in real time. So another challenge we have is the use of textual data. So defenders work with almost parsed data exclusively, and or there are systems in place to take their textual data and put them into a consistent format. Offenders don't necessarily do that. In fact, we don't really agree on the best way to represent our data as it speaks to payload generation, execution, or any aspect of our operation. Defenders also tend to get labeled data easier. So you think about like an email reporting button in Outlook when a spam email comes in. By the action of a user clicking report this email as spam, a label can get assigned to a data input and then be used to train models later on. So as offenders, we have to start thinking about labeling our data as we go through an operation or quickly after or shortly after. So expanding on this idea of feature engineering, which once again we kind of glossed over, this is really the magic of ML in my eyes, is you have a bunch of raw data and your feature engineering can sort of make or break your end model. We're trying to target important meta properties of the data itself, and domain knowledge, which I assume everybody in here has, is a great resource there. So when you think about a process list, knowing that process IDs increment in Windows or how they increment can be extremely valuable for extracting useful features. We generally just use basic statistics or sort of put on our data analysis hat when we're trying to design features up front. We could ask ourselves, like, what does the distribution of commands look like if we were trying to analyze them? We could ask, do new features line up with an existing label? So if we create a new feature and we have labels that we already know are, say, a sandbox or not a sandbox, do the features, even visually or when we look at it with our human eye, make sense? Are the features scaling properly, or do they seem to go up when a sandbox is there and down when a sandbox isn't? We want to try to reduce correlated features, called like feature noise, and we can do this before a model is trained or after. After it's trained, we would effectively just take the trained model and cycle features and see if it had an effect on our input or lack of effect. So once we think about our data and the data processing that we have to perform on it, then we're starting to design data pipelines. And I know obviously there are some projects at the bottom that detail this out. This is not a new problem to us, and we think a lot of people are working hard to tackle these challenges, but we're starting to think about how red teamers can build processes for managing our data. And these apply both long and short term. So there's a short-term process that is like op specific. So you might only run it when you're actually performing an operation. There's the long-term data that you ideally keep even after an op is ended, which speaks back to the point earlier about keeping data. This processing requires engineering. So we need to start early if we intend to train models later on. So if you are at all interested in ML, you need to start collecting this data now so that you have it later on. These implementations will vary greatly by team TTPs, so whether or not your tool is, say, multiplayer or single player could drive a lot about what sort of data you're extracting from it. It's ideally passive, so it shouldn't have an effect on the operators themselves, but it will reduce some agnosticism and likely tie us down to the system later on. This is like a rough abstract diagram of what I'm sort of talking about. Up top, you have the op period processes, so those are temporary. And we have our long-term collection over on the left. So we have our op running in the bottom right, very classic. We have operators who are interacting with a toolkit to run agents in a network. And we want to sort of strap on a data source to that toolkit and start almost exfiltrating data out of the tool as it flows between. So actions that operators are taking or actions that are occurring in the network. This could be something simple like a JSON file or a SQLite database or something more proper in the cloud. But after that, while the op is ending, or maybe when the op ends, we're going to transition it into a parsing layer. So this is where we anonymize our data. This is where we'd make it safe for storage. We also want to get different events that speak to different qualities of an op into a singular format. So we would want to maybe tag all of the actions that we could ever take in an operation under like a numerical category, and then we could start training off of that category using like the N label or the multi-label classification Will explained. We would store this data, and then we could train and test models to our heart's content after the fact, and hopefully we can glean some insights from those models and integrate it into our tools. And lastly, just a note about team integration. So development for these processes is going to be a requirement. Obviously, everything we've explained needs to be built somehow. We don't see this as an issue. We think people are really getting on this train of designing their own tools or their own supporting platforms for running operations. And it's helpful if you have access to the tool source code, obviously. Consider the trust in the final solution. Will has a saying that a model is made or broken by the ultimate results or trust in the results that it produces. So if operators are going to be using these results or these models at all in real-world ops, they need to be able to trust that the model is actually extracting useful information for them. You'll start with isolated jobs, like we went through sandboxes, which speak to like a binary classification problem. It's really simple. You could also do things just like statistics for ops, like average number of commands or the count and distribution of commands. All right, so now we're going to talk a little bit about attack graph theory and particularly the future of this as we see it. So there's a current state of attack path exploitation that's very standard. I imagine most people in here have used Bloodhound or at least heard of it. I certainly see some t-shirts. Neo4j is the base plane for this, and Neo4j is generally just an extremely powerful tool that we'll use as a reference for implementing some extensions on traditional Bloodhound theory. Bloodhound works great when you have all of the information available to you, but we believe that this information is going to degrade over time. So whether or not it's through changes in the underlying OS or Active Directory, the growing use of OSs that aren't as standardized, or even network segmentation that stops us from querying that data altogether, we're going to have to start making inferences about the relationships between objects without knowing them for certain. These networks are unknown, but they're discrete, which is good for our ML challenge. Effectively, we can say, well, we don't know the usernames, permissions, or all of the extended features of a network. We certainly know that it's not infinite, so we can sort of scope our problem that way. In terms of data inference, another nice quality of networks is that they require organization. So networks, as we think about them, are it's effectively a collection of assets, and we label them textually, and we organize them into clusters and put them in groups. So humans are organizing these networks. That way we know if we land in any network, regardless of its size or its origin, we can imply that there is data organization going on. We can then look at trying to infer relationships based on things like textual similarities. So the fact that SQL developers have SQL in their name, and they likely have access to SQL servers. We don't have to query those servers to know that, but as an attacker, I immediately know that SQL developers and SQL servers share a common term SQL that might tell me something about their relationship. We could also use like local host information, such as map drives, local users, or even external sources like LinkedIn or GitHub. You think about the number of people that put their job description on GitHub. So just parsing, or not on GitHub, LinkedIn. So you think about parsing LinkedIn, you could collect a potential list of users and their job titles and immediately start inferring the sort of groups or permissions they would have in a network, all without actually touching Active Directory itself. So this is almost a layout of what we mean when we say an attack graph without knowledge. It's discrete, so we know the end of the attack graph, but now we're starting to blend in this idea of fog of war. So we know where we are, and we might know the next few steps past us, but we ultimately don't know what true relationships are held in the network. So we can start exploring, say user A can take over user B, we get access and we try to pivot to host C, but we don't have privileges there. So we walk back and effectively explore alternative paths. Obviously, if we'd queried this network from the beginning, we would have all this information and we would know that the top path would not succeed and the middle path would. But now this process of subsequent querying is really going to drive the success of our models when we don't have access to all that information up front. So I imagine when most people thought about that diagram, they may be connected with this idea that as attackers, we build network maps as part of our day-to-day operations. We assume relationships based on our experiences in a network, or even pattern recognition, like we've seen configurations in the network that speak to X, so we expect those configurations to repeat. We act on these assumptions with queries. So we make an assumption, we have a prior belief, and we validate that assumption using a query. That's effectively all attackers do. We check access to a host, we verify group membership, or we collect new attack surface via that same enumeration process. So in many ways, we can be thought of constantly transitioning between assumptions and querying to validate those assumptions. Over time, this information creates confidence that we can use to state confidently the security of a network.
Cool. So now we're going to talk about simulating those mental models. So we have a model, and we kind of know the process that we go through mentally to get to where we want to go. And I've broken it down into effectively, we have a data layer. So the information from the current context. So let's say you fish somebody, you land on a host. You might have netstat information, for example. That's going to point to other hosts. So maybe there's a connection on there that points to intranet. So now without querying Active Directory, or you have some sort of information that you can then start to build these paths out. The next piece is heuristic search, or a heuristic rule, and this is operator driven. So it's like whatever, for example, those features or whatever those rules that you use as an operator to move throughout a network. This is that heuristic search. And then we can use simulation. So Monte Carlo tree search. We're going to go through a reinforcement learning example. But then we can start simulating these things out using graphs and probabilities. So if let's say we have 100 users, well, our probability is 1 in 100 for any given permission that it might be. And we can just go through and without creating the network, with the information we have, just simulate it out to the nth degree. And then the algorithm can backprop and then give us the best potential path we could take. It hinges on the heuristic. So if you don't have a great heuristic, you're not going to have a great model. And the simulation layer could be passive, but it could also be active. So when we say it can assist an operator in finding a path, we could also just hand it we could also put it in the driving seat where we allow it to execute commands and then infer output. So in the data layer, we just have your active host, your outbound RDP history, whatever it is that you're looking for. Or for example, Trevor really likes event logs. So he might have some particular thing that he's looking for in event logs that he's trying to correlate somewhere else. And so for him, he could throw that into as one of his data layers. Then you have a heuristics layer. So it's like, how can we relate that textual data? And then what strategies are used already? But effectively, we just need some number to support our simulation. So math requires numbers, and so we're always trying to go from text data, which is the challenge that we mentioned, into some sort of numerical value that is representative of our textual data. A heuristic, for example, could be just a simple if statement. I'd say this is the most basic, and it's the most flexible for people. So, for example, if your user, Billy Joe, and you do a getnet local group, and you see your user in the local admins group, you can just write a simple if statement that says, if my user in output, then sweet, I'm admin. So it doesn't necessarily require complexity, but if you're tasked with building out these rules one by one, it gets very difficult. So for example, you could use things like cosine similarity, where you're bringing in relationships, or you're projecting relationships onto a graph, and then you're looking at the distance between these 2 points on a graph. So effectively, again, we're in that one-hot encoding. We're just turning textual data into numbers, and then we're using cosine similarity to build, for example, something like this graph here. So this is a network of users, and they're clustered by their group memberships. So I just took their group memberships and then put them in as a string, and then now that becomes like the one hot encoding piece, and then we just cluster them. And so what's interesting is sort of this distribution where all the DAs kind of pile up in the middle, and this is fairly uniform across all of the networks that we've done it in. So if you imagine, let's say we've password sprayed or we have some credentials, before getting into it, or before starting to query, go down that path, you could, for example, look at the distance between any given user and your target user or a target host, and you could calculate that cosine similarity, and you could just take a sum of that, and you'd maybe get some reasonable assumption that this user is the best user to go after, rather than starting with like 3 other users that aren't useful to you. The second one, this is currently my favorite heuristic, and it's just Levenstein distance, and it's a string edit metric. But effectively, and I should say these are the queries that you can use in Neo4j to get this information. But effectively, it'll bring those SQL developers and SQL dev. It'll score those based on the edit metric or the distance, and it'll bring those relationships to the top. So rather than you having to go through and scroll looking for SQL servers, you could just run this against whatever information you have, And it's going that those relationships by design of the algorithm are just going to bubble to the top for you. Okay, so now we have heuristic, and we're just going to go into the shortest path, or simulation. So we have Dijkstra's algorithm, and this is the default in Bloodhound, and it's the shortest path algorithm, and it only goes one direction. So it's always going to find you the shortest path. But it's for GPS, so it gets you the fastest from point A to point B. We know and love it. Like it's awesome. Their talks, like the Bloodhound guys, have been, I don't know how long it's been out, the past 5 years, so they were well ahead of their time. And it's maybe kind of sad that it took us this long to catch up. So their talks are awesome. The guys are awesome. And it's useful for mapping, finding path problems. But it's not the only one. So for example, in an A-star algorithm, this is also in Neo4j. Let's suppose we want to apply a cost function. So imagine we only have 15 queries in a network before you're gone. So how do you maximize those 15 queries? What's the maximum distance you can get in 15 queries, and what are the best ones? So it might help us avoid particular paths. So for example, in Active Directory, you might get some relationship out, but network segmentation prevents you from actually exploiting it. And so a different algorithm like A-star might help you get around that in a reasonable way. But for us, we like, so that's the passive side. Now we're going to talk the active side in a Qlearning implementation. So Qlearning is like reinforcement 101. And I like it just because it is 101, but it can be really powerful with the right decision heuristic. And it basically says for a given action in a given state, the environment returns a new state and a reward. So you're an agent, and you're going to perform some action against the target network. That target network is going to give you back some output, and then from that you're going to infer, or you're going to give your agent some sort of reward. And typically, it requires like all the Q tables, as it's called, is initialized with all zeros. So it knows nothing about going in, which is suboptimal for us. Like we can't go into a network, learn it, and then hack it. We need to learn as we go. And so this is kind of what it looks like. So we have these state action pairs. So for example, in this case, we've used Levestein distance to pre-fill our Q table. So it already has some knowledge that we would already use. So we've pre-filled the Q table. So when it goes to select an action, it's incentivized to, it's incentivized by the reward. So it's going to see a positive reward. It's going to weight that action higher. So versus an action that has 0 points. So in most of your Levestein distance, if you use it, it will be 0. So effectively, we'll select an action, and the environment will give us some output. So on the right, you see directory of, and we give it some reward, and then we just refill the Q table. This is useful when it's all zeros. But it's like you can have all your states and all your actions. So for example, here we have shell on SQL dev. So it's not just an admin. You can set whatever states you want it to be. And then you can set any number of actions. So for example, if in your toolkit, if you have 99 commands, you could just take every host, like if you want to do ls, an action would just be ls for every single host. And then you would have some entry in the Q table. So when it does that, whether or not it was successful, it would look. So super awesome. Actually, this is also at B-side. So there's a script out on my GitHub called opbot, and it's the basic implementation or a combination of reinforcement learning and Levestein distance. Super awesome. There's a ton of other algorithms that you could potentially use. So for example, Dempster-Schafer is just like the theory of evidence that came up. But effectively, we're just all data processors. Like that's literally all we do is we just take in data, we filter it, we come up with some reasonable assumption, and then we make a query. Attack graph theory, we think, is the future, especially now that we're going to need to start inferring data as our access to data goes away. But heuristic-based cyclic queries are a black box. So they're not a guarantee. So there are no more guarantees in a world where we don't have information, where we have to infer. So there's no precise probabilities. There's nothing like that. So we just have to rely on our domain knowledge and our heuristic search to make up for that fact. And given you can go look at the script, but we're going to get into the next more exciting bit because we're running out of time.
All right, so we've kind of covered a collision course, like a case study, where we looked at sandbox detection, we looked at some data processing, and then the last section was primarily talking about operating, so offensive ML applied to doing what we do as operators. And it's just a note that that Qlearning process with Levenshtein distance of, say, LSing hosts is not unlike what many operators would do. But now we're going to get into adversarial attacks, which we're actually pretty excited about. So adversarial ML is attacking existing models. The definition varies. I've heard it described generally as just the application of an adversarial mindset to ML. But it's the same stuff, different day. Essentially, ML is coming about and it has a focus on effectiveness and efficiency. So that's the metric by which they judge the usefulness of a model or the utility of a model. Models are not designed to be secure or robust. So there's this growing field in ML where we're realizing that we're designing models to solve problems, but we're not making them resilient against attacks against those models. This has all been proven mainly in the lab. It's not necessarily theoretical, it's hard to build. Many of the demonstrations that we've seen and that are public lack practical use. So maybe in most cases they're creating a classifier and then creating a generator and then pitting them against each other, but they built both halves. There's two basic approaches to this, a white box approach where we have access to the original model, the architecture, the features. We effectively have a lot of insight into how we might best attack that model. There's the black box, which is the alternative approach where we only have access to the outputs. So we can give it an input and we can get outputs, but we don't have a lot of insight into how it's actually creating those, although we can make some reasonable assumptions. There's a lot of previous works here. So Deep Word Bug was a black box generation of adversarial text. The guys at Skylight Cyber looked at reversing a client-side model to bypass silence. There's also a robustness toolbox from IBM that discusses not only common attacks that are used for adversarial ML, but also defenses. So it's just a great reference point for a lot of the algorithms that are being applied to attack these networks. But for our case study in this regard, we're actually going to look at an email security company called Proofpoint. They represent about 230,000 domains based on my analysis of the Rapid7 Sonar data. It includes 590 government domains and a little over 2,000 educational domains. They openly promote their use of ML, so you'll see the terms MLX and CLX used in their data sheets a lot. These refer to their generalized ML model, and CLX is their closed loop system used for customers. So about a year ago, Will came to me and he was doing some testing in the email gateway on an op, and he noticed that scores were included in the response headers from an email in Proofpoint. So effectively, as the email had transited through Proofpoint, it had embedded its scores into the header of that email. And we've highlighted them there. There's obviously a lot of them, but these leaky inputs create an opportunity for us to attack this model. So essentially, we have control over the inputs, and now we can gain access to their outputs. So we have a few theoretical attacks we can lay out based on this. Step one, we need to collect a data set, and this data set is our data set. So we're speaking to the fact that we would need to send some X number of emails to steal scores and line them up. We ideally want this data set to be as big as possible, but we might be limited there. Two is to copy the model. So this is effectively, we're going to build a copycat model based on those inputs and outputs so that we have effectively a little Proofpoint clone model. So we want a model that we can play with and extract insights from and use offline that reasonably represents the Proofpoint model as it stands inside of their network. The 3A attack would be to extract info from that model manually. So we like this attack particularly for the use of writing phishing emails, as it means that we can get actionable insights from the data really quickly. But we could do really basic approaches like take the n highest lowest emails and unique their words, or toggle inputs to discover the most impactful tokens. And something like that would look like this, where we take emails in and we get back a scored data set. We pipe it into a copycat classifier and extract those insights. Attack B would be the same process for 1 and 2, but we might make a generator to effectively learn the insights itself. So we effectively build a generator and we say target the maximum score and play against this classifier until you can generate content that's reasonably able to bypass, Proofpoint spam filter. 4 would be to automate those improvements. So we could use the generator to fix our candidates or to just generate good content from scratch. And that attack looks like this. So there's some clear challenges here when me and Will first started talking about this. First task is we need some initial email content, so we have to find a sufficient data set for sending in inputs. I don't necessarily have 10,000 emails laying around. you could send in something like Wikipedia articles, but we want it to be representative of the like email lexicon. We want it to be grammatically similar to emails that we would type. We have the issue of bulk email delivery. So we need to send in these emails and collect scores. The scores themselves are applied after they transit through Proofpoint. So it's easy if we have a Proofpoint inbox because we can simply send the emails to ourselves. It's much harder if we don't. And in terms of final outcomes, if we do the generator approach, it will likely create somewhat gibberish that's going to require human intervention to actually make useful. And bypassing this model is obviously only one part of the total defenses that we might need to get past, including like user action or sandboxing of the payload, or even link rewriting. So in terms of collecting a data set, we chose effectively 2 data sets to send in, and we're going to refer to these as like our text-based candidates and our link-based candidates. Our text-based candidates were from the Enron data set, and this is a really common data set used for like spam ham classification. And our links are the ISCX URL dataset, which is pre-classified. We just took a random sampling of these links and sent them in, because ultimately we don't care about the fact that they're pre-labeled. We used bouncebacks to collect the scores, so we delivered the messages through Mailgun and received them into an S3 bucket. And in our collection runs, effectively the 2 primary ones are we sent in 13,000 links inside of a generic template, and we sent in 15,000 raw subjects and bodies that cloned the Enron inboxes. So the attack sort of lays out like this in a technical sense. We effectively post an email candidate to Mailgun, which delivers it to Proofpoint. Proofpoint will score that candidate and add in headers to the email. Then we're effectively delivering the message to a non-existent mailbox at a domain that sits behind Proofpoint. So by the time the message hits the target mail server, it will effectively bounce back the return path to our Amazon S3 bucket, where we can extract the data and we effectively have scored emails. So after we did this, we opened this up and effectively started looking at these scores to try to make sense of them. Once again, there's 13 scores that Proofpoint embeds in their headers, and we weren't really sure which ones were valuable to us. We can immediately see some of them stand out, like priority, MLX, log, and CLX. And once again, we can see that those line up with the datasheet terminology that we saw prior. We did some basic correlation on these scores to try to discover a score that speaks generally about the security of an email. So if we see a score that's at least seeing some correlation with other scores, then it probably means that as other scores are changing, this score is changing as well. So it spans, some score set, so to speak. So the MLX log stands out to us. It has relationships to spam, phish, and the core MLX. And we can also see their generalized score has like a 1-to-1 to their spam score and a 1-to-1 to the MLX score. So we took the MLX score and we laid it out in a histogram to check out distribution. In terms of our text-based sampling, it's definitely leaning more towards the right. Effectively, we have a lot of candidates that were scored 999, which as far as we're aware is like a perfect score. But when we analyze our linked targeted samples, we'd see a much better distribution. So we can see that our links are hovering around the 500 mark, and we get a really nice curve out of it. Another good thing is if we took these raw MLX log scores and actually line them up in an ordered fashion, we actually see the sigmoid curve that effectively proves that we're seeing activation of these scores.
So obviously the first step is to copy a model. So just going out, you can look what are some likely candidates for how do people do spam ham classification. And we went out and we just built these models in Keras. So we built an LSTM, and then we built a regular neural network, just like the one you saw earlier as a sandbox. So it's not any different. And then we just selected the label for the MLX log score. We just felt that that was the most general. And our data kind of supported it. And we found that generally values were between 1 and 99. That wasn't true. So it seems like in their data set there's some like hard-coded values, so like 10, 15 is for outbound emails, is what you'd almost always see. And we came to the fact that larger equals safer. So traditionally you would say on the flip side, lower is usually safer, but it really doesn't matter. It's about the activation. And so what we did is we created those models, and then we just trained them on Proofpoint's outputs. So we vectorized our inputs, and then we just used that regression to target their output score. So our model is effectively, we just want to get as close as possible to their output. So it doesn't matter what it is, whether it's a Wikipedia article or an email, we just want to make sure that our classification is close to theirs, whether it's correct or not. And so these are kind of the results that we got. And these are points. So on a scale of 0 to 99, if, for example, we predicted a 400, or if Proofpoint, sorry, predicted to 400, we'd be within 42 points of their score. And so, this was consistent across all. But obviously we see the neural network. I kind of thought the LSTM would do better just based on sequences. But the neural network with a bag of words it was incredible. And even 42, like we're within 42 points of this spam filters on average. So it's a mean absolute error. So on average, we're 42 points away from their predicted scores for links, and then 69 points away. So it effectively means we just have their model pegged, at least to a certain extent. So attack these to kind of gain insights into our model. So now that we've confirmed that our model is good and we have a decent offline copy, we can start to play with emails and we can start to build attacks that will bypass their filter. And so, for example, we could take a phishing email, click here for cats. We could make misspellings. We could remove words. We could, anything we can do to change that score, and then we can just submit it to our copycat model and then get some reasonable. We chose the toggle inputs, so we basically just toggled those values on and off so we could find. And then we scored we could score every possible combination of tokens. It's a bit like fuzzing a network, so you just take all your words and then just turn them all off. So until you get everything. It's pretty computationally expensive. But effectively, to extract information, to get sort of like good words or bad words out, we make a base prediction, and then we just go through and alter those and alter the tokens, and then we make a new prediction, and then we just add it to a rolling list until we got just a list of words that we were able to pull out of the model. So these are the good words. So these are the top 10 words that Proofpoint's model think are good. So if you add these top 10 words to your email, you get 9999. These are they're kind of in the middle, and then these are the bad ones. So there's a slide in a second. So this is for text. So this is just for emails. And then these are the ones for links. And so if you have these words in your links, you get top scores. So if we look at confirming the insights for our texts, so the top 10 highest scoring words got 999. The random 10 words in the middle got about 640, so ideally we'd be trying to hit 500 or 999 divided by 2, so whatever that midpoint is. But the top 10 lowest scoring words, it didn't even accept it. So it said, this looks too much like spam, we're not going to accept your email. So for us, that was like, yeah, we know it's spam because you told us it was. And then for the links, it's the same thing. So our prediction, 378. The real is 300, and these are just come from all the good words and the bad words. So we effectively just stole Proofpoint's model that we have offline that we can just do whatever we want with now, and we can play with emails, we can bypass our filter, and we have a list of good and bad words that we can just add. So you could potentially add these to an email, make the text white, and there you still have your phishing email. So that's one attack. But so in terms of disclosure, we haven't told Proofpoint this. We just know now. But it's different. So models are interesting. They represent a learned vector. It's not like a lol bin or an exploit that you can just patch. They're trained. So it's like, I don't know what Proofpoint's process is to retrain their model on their data set that they have that we effectively stole. So the retraining process is just going to be very difficult. They can obviously stop leaking outputs. That would be probably the good first step. But our model is going to degrade over time. So as they retrain their models daily or whatever their process is, like we have some window to use this model. But as long as they keep their outputs available to us. Okay, so then what percentage considered a viable bypass? So at what point are we like, yeah, we can bypass 50% of the time. We're going to tell you about it. It's not like we can exploit RDP. You just can't add a signature. So some final thoughts?
So just to put this in context, obviously application whitelisting, got popular 2 or 3 years ago, and it effectively was just a vendor pitch as long as it got sales. Like I see vendors in Black Hat now that used to have app whitelisting on their vendor board, now they don't, and now they're touting ML. It's the same vendor, so I'm wondering what exactly their product does do. And another thing Will enjoyed was Endgame put out a competition to give a GPU to anybody who could bypass some static sample analysis. And the winner just added emojis to all of the samples, like in the headers of the file, and bypassed it. So these data scientists are solving defensive problems, and they might not necessarily have the domain knowledge to accurately, create secure and robust models. And Will's statement is, if you don't understand X before ML, you probably won't stand it or won't understand it after.
But it's not all bad. So we can obviously use this. So in the future, I'm thinking of intelligent agents. So you're pushing models client side. So for example, because the model is just weights and math, you could write all your weights to an Excel sheet, and your model goes with your payload. So you no longer have to make a web request. Genetic programming client side, so you could come up with new strains of malware client side using JIT. Rootkits. So we're just going to go lower into the OS. But effectively, we do want to help vendors improve their products and make sure that this isn't just the next issue that we're going to see. Application-wise thing, it was cool until everybody realized there was a ton of stuff that could execute things. So these are some other fun projects. So what other defenses that leak outputs? Windows Defender, email attachments. My dream is to have like an email chatbot or a LinkedIn chatbot that that'll feed you a document. So it's going to warm you up as a chatbot, and then it's going to send you a document at some point. Or you could just add data extraction to Neo4j. Ultimately, it's a ton of fun, like just pressing enter and watching your model train and see how it does every time. Machine learning's here to stay, so don't sleep on it if you're on the red side. It's all funny until, it's all rebranded if statements until you get caught by it and you don't know why. Model bypasses are going to become part of all offensive toolkits. They're already part of ours. And ML understanding could just quickly become a job requirement, especially if you're going to operate into the future. Let's say 3 to 5 years from now, it could very quickly become very useful. So I'm like a little speaker box at the office. Everyone's sick of me talking about ML. But it might be nothing, and it could be everything. It's likely going to be somewhere in the middle, but only time will tell. Like, it's here to stay. It's going to mature, so it's worth your time to invest in it. So I just want to say some thanks to some people, and we are out of time. So you can come find us after. Code will be up at the end. As we do, I do want to thank Nancy Fulder of BYU for providing guidance, and all of you for obviously attending this talk. Thank you.